Hi everyone. This video presents our UCS551 Introduction to Data Analytics project entitled Allowable Concrete Strength. In this presentation, we will demonstrate how the data analytic and supervised machine learning techniques can be applied to predict whether a concrete mixture satisfies the allowable strength requirement. We will also explain the data pre-processing process, the development of different classification models, and compare the performance to identify the most accurate and reliable model. We hope you find this presentation informative and enjoyable. Without further ado, let's begin.
The first member of our team is Nurul Fadlin Hamimi binti Kiprawi with student ID 2025304983. The second member is Muhammad Afiq bin Muhammad Hussein 2025164593, and then me, Fidelis Igai and Alexander 2025167075. The last member of our group is Roy Edison Anna Edward 2025921319.
Concrete is one of the most widely used construction materials in civil engineering due to its strength, durability, and versatility. It is commonly used in the construction of buildings, bridges, pavements, and many other infrastructure projects. One of the most important properties of concrete is its compressive strength, as it determines whether the concrete is suitable for structural applications. However, the conventional method of evaluating compressive strength requires laboratory testing after a specified curing period, making the process both time-consuming and costly. Wait, why we are talking about concrete and why suddenly machine learning? As mentioned earlier, conventional laboratory testing of concrete compressive strength is time consuming and costly because it requires a curing period and specialized equipment. Therefore, there is a need for a faster and more efficient method to evaluate whether a concrete mixture satisfies the required strength. With the advancement of data analytics and machine learning, it is now possible to predict the strength of concrete mixtures based on their material composition. Therefore, this project provides machine learning techniques to classify whether a concrete mixture satisfies the allowable strength requirement. The objective of this project are to analyze the characteristic of concrete compressive strength dataset and identify the variable that influence concrete strength performance. To perform data preprocessing using ETL, which is extract, transform, and load process, to clean, prepare, and transform the dataset before modeling. To develop supervised machine learning classification models for predicting whether a concrete mixture satisfies the allowable strength requirement. To evaluate and compare the performance of different machine learning models using various data splitting strategies and cross validation techniques. And lastly, to identify the most accurate and reliable classification model for predicting concrete strength suitability based on the prepared dataset. The dataset used in this project is a publicly available concrete compressive strength dataset. It contains numerical information describing the proportions of materials used in concrete production, together with the corresponding compressive strength measurements. After the preprocessing stage, the dataset was transformed into a classification dataset by introducing a binary target attribute called allowable, which indicates whether a concrete mixture satisfies the required strength requirement. Although the original dataset contained more than 1,000 observations, only 235 clean records were retained after preprocessing for the modeling stage. The dataset consists of 9 attributes, where 8 numerical attributes such as cement, water, aggregates, and curing age are used as predictor variables, while allowable serves as the target label for classification. Before developing the machine learning models, we first assess the quality of the original dataset to identify any issues that could affect the model's performance. During the assessment, several data quality issues were identified. This includes missing values, duplicate records, outliers, and the need to transform the original target attribute into a classification label. Missing values, particularly in the cement and blast furnace sludge attributes, were handled using appropriate imputation techniques. Duplicates records were removed to prevent bias during model training, while outliers were carefully examined to determine whether they represented valid engineering measurements or data entry error. In addition, the original concrete compressive strength attribute, which was recorded as continuous numerical value, was transformed into a binary target attribute called allowable. This allowed the dataset to be used for supervised classification. After completing the data quality assessment and pre-processing, the final dataset consists of 235 records and 9 attributes with no missing values, making it suitable for predictive modeling.
Data pre-processing. The pre-processing stage prepares the raw concrete dataset for machine learning by generating the target label, removing duplicate and invalid records, replacing missing values with the mean, selecting the most relevant features, exporting a clean dataset ready for training classification models. Step 1. Data extraction. Import the dirty concrete dataset from the data repository. Load the raw dataset containing missing values, duplicate records, and inconsistent data for cleaning. For second step is attribute generation. Create a new grades attribute by categorizing concrete compressive strength into standard concrete grades, for example C20/C25, C25/30, C30/40, C40/50, C50/60, or C60 plus. Generate a new allowable attribute as the target label. Yes for concrete compressive strength, which is equals to or more than 20 MPa. No for concrete compressive strength, which is less than 20 MPa. The third step for data preprocessing, remove removing the duplicate records. First, we need to identify and remove the completely identical rows so that we can prevent data redundancy and reduce bias during model training. The next step is data filtering. Apply filtering rules to retain only valid concrete mixtures. Remove records where blast furnace slag equals to 0, fly ash equals to 0, and super plasticizer equals to 0. Ensure only meaningful samples are used for analysis. Fifth step, handle missing values. Detect the missing values across all selected attributes. Replace missing values using the mean, which is average, value of each respective attribute. Preserve all records without deleting incomplete observations. For step 6 is the feature selection. Remove unnecessary and intermediate attributes. Retain the 9 most relevant features for classification. First one is age, cement, water, blast, furnace slag, fly ash, super plasticizer, coarse aggregate, fine aggregate, and allowable target level. Step 7. Target level assignment. Assign the allowable attribute as the label target variable. Prepare the dataset for supervised machine learning classification models. Step 8. Data storage and export. Save the clean dataset and rename it to Clean Concrete Repository, and then export the final dataset as cleanconcretemis.csv. Produce a standardized dataset ready for training and evaluating machine learning models.
Next, we are going to talk about data modeling. Now we are
Next,
going to
we are
explain about data modeling. So what is data modeling? Data modeling is a process of creating a visual representation or a blueprint of entire information system or parts of it to communicate connections between data points and structures. It standardizes how data is collected, stored, updated, and organized across an organization. In data modeling, we are using three modeling processes, which are split ratio model, k-fold cross-validation model, and lastly, combined model. In each three modeling processes that we are used, there are three classification process that are included inside the modeling process, which are naive Bayes, logistic regression, and random forest. So what is naive Bayes? Naive Bayes using a probability or a naive Bayes theorem. Logistic regression is to use to predict the probability of a data belonging to a specific class, which is binary and multi-class classification tasks. And lastly is random forest, which use many decision tree models to make a prediction. So for our split ratio model, we are validating the performance by randomly dividing the data into non-overlapping training and testing, which is training 70 until 90%, while testing is 10 until 30. So it should be like 70, 30, 80, 20, and 90, 10. This project evaluated the machine learning model across three specific split ratio that I mentioned just now. This is the split ratio model. In order for us to produce a split ratio model, all we have to do and all we have to need is the retrieve clean dataset. So how do we get the clean dataset? Clean dataset is the one that we obtain from our data pre-processing process. So in this model, we're using the clean dataset. Then we put a split data operator. This split data operator is the one that we are going to use to train and test our data and model. As you can see, we are using two multiply operators, which is one for machine learning and one is for apply model, which we can see at the bottom and the above. In the multiply machine learning, we split it into three, which include naive Bayes operator, logistic regression operator, and lastly, random forest operator. On the multiply apply model, we can see apply model naive Bayes, apply model logistic regression, and lastly, apply model random forest. For the classification that we are using classification performance for each of them, which is classification performance for naive Bayes, logistic regression, and lastly, random forest. Just like as I mentioned before, for the result, we are testing for 70-30 training and testing, 80% testing and 20% testing, and lastly 90% training and 10% testing. Next, we are moving to the second model, which is the k-fold cross validation. So what is k-fold cross validation? It is using the k subsets, which iteratively training on number of k faults and testing on the remaining faults until all are used. This is to reduce the overfitting and offers more dependable evaluation than a single train test split model. So these are the cross validation model that we are using. As usual, we are splitting them into three, which is for knife Bayes, logistic regression, and lastly, the random forest. Lastly, we are talking about combined model. What is combined model? Combined model is basically a combination of two of the model just mentioned just now, which is the split ratio model and also cross validation model. We are combining this so that it is to perform a single dataset into parallel streams, which enables fair side-by-side performance comparison in a single run. This is the combined model, which has a lot of operators used in order to make a combined model. As you can see, above is the split ratio model, while below is the cross-validation model. But in the end, it is combined in one performance operator, which can lead to the same output.
Next, I will present the results of our machine learning models. We evaluate three different classification algorithms, which are logistic regression, naive Bayes, and random forest. Each model was trained using a concrete strength dataset and test using different trend test permutations. The purpose was to compare the prediction accuracy and identify which model is the most suitable for classifying allowable concrete strength or to predict the allowable concrete strength. You can see here, naive Bayes. It's more to the probabilistic estimator, and for logistic regression, it's used the linear separator, and for the random forest, it is the ensemble network, which is it use many decision tree. Next, I will talk about split ratio dynamics. This slide showed how the models perform under different trend test split vectors. We found that the random forest model consistently achieved the highest accuracy, especially when more data was used for training. This is because random forest can learn complex relationships between the input variables more effectively. On the other hand, logistic regression showed a slight decrease in performance when the testing data becomes smaller, indicating that it is more sensitive to the data distribution. You can see here the random forest advantage. It's increasing the training population directly, relative accuracy. More data allows this to capture unique structural pattern. And for the logistic regression, Its performance decreases as the testing full string indicating its favor a larger testing proportion to validate its sig model probability threshold. Now I will talk about cross-validation stability. To ensure our results were reliable, we also perform cross-validation. Cross-validation evaluates the model using different subsets of the dataset, reducing the possibility of biased result. The result show that random forest and logistic regression both maintain accuracy above 95%, demonstrating strong generalization performance. Although libraries improved with cross validation, its overall performance was still lower than the other two models. You can see from the graph, although the naive bias, the data of the percentage of naive bias is increasing, but it is still lower than other two machine learning, which is random forest and logistic. Next is model synthesis and final verdict. So after comparing all the evaluation results, we considered both prediction accuracy and model stability. While logistic regression performed well and naive bias was simple and efficient, random forest achieved the best balance between high accuracy and consistent performance. Therefore, random forest was selected as the best model for predicting allowable concrete strength. As you can see from the table and the slide, for peak slide data accuracy, the highest is from the random forest, which is 100%. And for the cross validation, the highest still between random forest and logistic regression, but overall, the random forest is the winner. So why random forest wins? The main reason random forest is our preferred model is because it can capture complex relationships between concrete materials and their properties. It achieved the highest prediction accuracy of 100% and maintained a cross-validation accuracy of around 95.7%, and showing that the model is both accurate and reliable. This demonstrates that machine learning can support engineers by providing fast and dependable predictions, reducing the need for repeated physical testing.
To conclude, this project successfully applied supervised machine learning techniques to classify whether a concrete mixture satisfies the allowable strength requirement based on its material composition and curing age. Before modeling, the dataset underwent the ETL process to improve its quality by handling missing values, removing duplicate records, and transforming the target attribute into a binary classification label. Three supervised machine learning models such as naive Bayes, logistic regression, and random forest were developed and evaluated using different split data ratios and k-fold cross-validation techniques. Based on the evaluation results, Random Forest achieved the highest overall performance and was identified as the most accurate and reliable model for this classification task. In conclusion, this project demonstrates that machine learning can provide a faster and more efficient approach for evaluating concrete strength, supporting engineers in making better decisions while reducing reliance on repeated laboratory testing.
Let's conclude our presentation. Thank you for your attention. We hope this presentation has shown how machine learning can be applied in civil engineering to predict allowable concrete strength more efficiently and accurately. Thank you.